All right, so welcome to the last week of Cal 2, right? And we have our final, next Thursday? Thursday at 12:30. We'll talk about the exam on Thursday. We are going to try and finish up 8.6 and 8.7 in the next 2 days. We won't see Chapter 9. I still have to figure out, I'm offering a bonus lecture. I've been kind of throwing in the air whether or not I'm going to do Chapter 9 stuff or if I'm going to do the Fourier series like I had initially intended on doing. So I don't know yet. Yes?
How many points is it?
I don't know. I'm thinking like 5 points on the final.
Final grade?
5 points on the final exam. But I need to still determine the time. So let's finalize that on Thursday. All right? How many of you would want to do it like this Friday?
Thursday?
Mm-hmm. Think about it. This Friday versus next week sometime. Think about it. All right. So 8.6, if you were here a little while ago, I usually write the word focus on the board every time, right? But I wrote intense, like today is going to be pretty intense, all right? So please follow along, ask questions if you have them, but you're probably going to feel a little bit like, what's going on here? Maybe, I don't know, we'll see. So this section is called Representing Functions as Power Series. Last section, what we did is we looked at what a power series was, and we figured out how to determine the radius of convergence and interval of convergence of a power series. And what did we use to do that most of the time? The ratio test, right? We're going to kind of step away from that now, and we're going to see how we can represent functions with power series. So we take a function that we're familiar with, but instead of writing what we're familiar with, we represent it as a power series instead. And so the question becomes, why would you ever want to do that? Right? Why would you ever want to represent a function that you're happy with a power series? So take a look at this integral here. This right here we would call the integrand, right? That's the thing you're trying to integrate. And we could consider that to be some function of x, right? If I asked you to integrate this right now, I could leave you to it and you would do your best, right? Whatever you would do to integrate that. Let me show you what Wolfram alpha does, all right? Oh, it's just that right there. It's just a mess, right? That's not very pretty. Would you agree? So maybe we could get it, right? Maybe we could. Yeah? But integrals, as we saw, integrals are used to find, when we first talked about like what's the use of an integral, it was the area under a curve, wasn't it? And so what we would want to do is find the antiderivative and then plug in the endpoints and get a number, right? A numerical answer. And in the real world, numerical answers only have to be as precise as we actually need them to be. You know, if you're putting a lug nut on your tire, on your wheel, on your car, there's a certain torque, right? You know, whatever it is, 100 foot-pounds, you know what? 110 usually foot-pounds, right? That's what you need for the torque on a bolt. You could put 105 and probably be okay, right? But if you're torquing down a bolt on the engine mount for an airplane, you probably need to be dead on what the manufacturer says, right? There's a certain give and take, understand? And so with an integral, we just want to get a numerical answer. And sometimes we don't need it to be exactly dead on to the true answer. We just need to be close. And how close? Well, depends on if it's a lug nut or an aircraft bolt or a car bolt, right? So I don't know if this is making any sense. What we're going to do instead of looking at this function, which is very difficult to integrate, as you can tell, Wolfram alpha had some trouble with it, right? Well, it got it, but it's a lot of shit that we wouldn't want to spend time on, right? So maybe we just need to get close. So what we do is we rewrite this function as a power series. And remember, power series were just a bunch of powers of x, weren't they? And if you integrate a bunch of powers of x, it's very easy to integrate, right? If I give you x to the fourth, everyone could integrate that? 1/5 x to the fifth. So if I just have a bunch of powers, you could integrate that pretty easily. And then you would plug in your two limits of integration, get your numerical answer. And of course, you couldn't go all the way out in the series, could you? But how far would you go out? Well, as far as you needed to be close enough to whatever it is you're doing. So that's the focus of today. How do we approximate a function with the power series? We will answer this question in a little while. We're not ready for it, okay? We will get to this. There was another one I wanted to show you. I'll put it up on the board for my internet students. Arctangent of x over x dx. If you were asked to integrate that. So let's ask Wolfram alpha to do that. Arctan x over x. Looks pretty harmless, right? Oh, okay. It did spit out an answer. The answer looks pretty clean, right? Can you all see it? That's the answer. 1/2 I Li sub 2 of negative Ix minus Li sub 2 of Ix. What is that? Well, it says down there in the corner, Li sub n of x is the polylogarithm function. What the hell is a polylogarithm function? And those are imaginary numbers? Okay, so we're not even ever going to get that, ever, in this class. All right? So there are some things, moral of the story, that we cannot integrate easily, but we still want to be able to integrate. And so the power series is a tool that we use to get around these difficult integrals. All right, this was the difference between Leibniz and Newton, the two fathers of calculus. Newton had power series. Leibniz didn't have power series. He didn't get that far with the calculus. So there were certain integrals that Leibniz couldn't do that Newton could do. And I think for that, Newton is, to me, it's my opinion. I think Newton's version of calculus was a little more powerful. All right, so today we are going to be using extensively the geometric series, which I put up here. Just as a reminder, because I'll keep pointing to it, and just so it's on camera, we say that the absolute value of u, if that's less than 1, then the sum n equals 0 to infinity of u to the n, which is 1 plus u squared forever, should converge to 1 over 1 minus u. That's geometric series. Here we're using u instead of r, and a is 1. All right, we know this is true. Yes, you agree? All right. With that simple formula, we're going to do some crazy shit now, okay? All right, here we go. Let's start with this. This is gonna get, increasingly difficult as we move through the class. So what we want to do first in this example is express this as a power series. And I want us to also find capital R, which is the what? Radius of convergence, right? Not the interval of convergence. The interval of convergence is a little more involved, isn't it? Because what does the interval of convergence require that the radius of convergence does not require? That you check the endpoints, right? That's the difference between interval of convergence and radius of convergence. So this will be a little easier for us to do. So here it is. Here's the function. F of x equals 1 over x plus 5. Now, I think we would all agree, hopefully, that that's a pretty nice function. Like if I plug in 1, it's pretty easy, 1/6. Plug in 2. Like that function is well behaved. If I were to ask you to integrate that function, you could do that pretty easily too. It'd be a natural log or something like that, right? Not a difficult function, but we're starting simple, we'll build, all right? So can I express it as a power series? This is the only thing I've got right here. This is the only thing that I know, this thing right here. I know that this right here, anytime I see this expression, can be rewritten as this series, can't it? as this power series, as long as the u that I had, absolute value, is less than 1. So the question is, can I rewrite that to look like this? So let me show you. First, let me just change the order on the bottom. I'm going to put my variable on the right side because in this form, the variable u is over here, right? I have a 1 minus a u. I don't even, not even close, right? 5 plus x. What about this? Factor of 5 out of the bottom. Okay, so if I distribute this 5 back through to these two terms, I would get this back, wouldn't I? Yeah? And then I just peel the 1/5 out in front. So we good on this, on that so far? Yes, we're good. We got it, sir, no problem.
We're good.
We're good? Okay. Now, I need subtraction. I don't have subtraction. I have addition. So I'm going to add the opposite, like add a negative. So 1/5 times 1 over 1 minus, in parentheses, negative 1/5 x. That's a 5. We still good?
Yes.
Thank you. All right. Do you see now that we have 1 over 1 minus u? Yes? Now we have a 1/5 in front, but don't worry about that 1/5. The u for us is this, isn't it? That's the u. And so as long as the absolute value of this piece right here is less than 1, I can rewrite that with this power series, can't I? So that's what I'm going to do. So if the absolute value of negative 1/5 x is less than 1, then 1 over 5 plus x, which was the original function I was looking at, right, can be rewritten as a sum n equals 0 to infinity of what? Of what? U to the n. But what's u? Negative 1/5 x to the n. Do you agree? Understand that? Yes.
What about the 1 over 5?
1/5. Yes, thank you. This 1/5 right here. Thank you for catching that. I forgot to put the 1/5 in front. Let me move this over. Okay. That better? All right, so this is a power series representation of this function. It is. But we want to make sure that we are comfortable converting it into what a general power series looks like. So remember what a general power series looks like. It's like sum n equals 0 to infinity, c sub n, x minus a to the n. That's a general form of a power series, isn't it? So what we try and do is we try and peel off the part that's the number that's going to keep changing. Possibly it might be the same the whole time. And then we want our x minus a constant to the n power. Right here, I don't have x minus a number to a power. I have negative 1/5 x, don't I? So what I'll do is I'll peel that apart first. So watch me do this. So this is equal to the 1/5 out here, okay? Sum n equals 0 to infinity. Now let me see how comfortable you are with this. Negative 1 to the n times 1/5 to the n times x to the n. So what did I do there? Peeled everything apart. That's right. I realized that that's the same as negative 1 times a fifth times x, right? All to the n power. And then just did the power on each one. Is that okay? Now, the reason why I peeled the 1/5 away from the -1 is because I have a 1/5 out here. Can I bring that 1/5 back in? What do you think? This is remember, this right here is a bunch of things added together, right? The 1/5 would distribute to each one of those, wouldn't it? So it can actually be placed back into the series. So I'm going to put the 1/5 in here next. Let's see, sum n equals 0 to infinity, -1 to the n. What happens when I take 1/5 and I multiply it times 1/5 to the n? It's 1/5 to the n plus 1, isn't it? Now these are things, if you've been doing your homework, hopefully you've picked up on. 1/5 to the n times 1/5 to the first power. You add the two exponents, you get this, right? And then I still have out here what? X to the n. Right there. Now, do you see that this is more like the general form of power series? Do you see this part is your C sub n, and this part is your x minus a to the n? Y'all see it? That's the way the book's going to write it in the back when you're looking to check your answers. They're going to do this part. They're not going to stop here. They're going to go to this. Any questions? None?
When you distributed the 1/5 back in, that's assuming that you simplify it as much as you can, right? So you put it back.
What do you mean?
That second line up there.
Here?
Yeah. When you said you're going to put the 1/5 back in,
Yep.
that's assuming that you simplified that as much as you can.
I could have left it in here the whole time. I could have. Like, I could have put that 1/5 right there. But if I want to peel the x away from everything else, then I'm going to get the 1/5 eventually to come together. Saw another hand. No?
No, we got it.
Got it? Yes?
You said if -1/5 x absolute value is less than 1,
Mhm.
we can do that by just looking at that. Like 1/5 is obviously less than 1. But for something that's a little bit more involved, we would have to kind of do more to that portion instead of just
Well-
looking at it and saying, oh, that's.
No, I mean, we don't need to do any more to this in terms of like, this is the inequality we set up. There's nothing more to set up. But we do need to find the radius of convergence. And remember, the radius of convergence comes from this expression right there, right? So that's what I need to do over here.
So you're not done yet.
So I'm not done yet. This is the power series, okay, that represents that function. And now I want the radius of convergence. So for the radius of convergence, I come back to this inequality, and I split this up. The absolute value of -1/5 x is the same as the absolute value of -1/5 times the absolute value of x. That needs to be less than 1. What is the absolute value of -1/5? 1/5. And then what do? Multiply both sides by 5. So the absolute value of x has to be less than 5. So what's my radius of convergence? 5. So r is 5. Okay? Any questions? This is about as basic as it's ever going to get right here. Just for the sake of seeing it, what is this power series? Give me the first few terms of this power series. So like let's let n be 1 and then 2 and then 3, and let's just write out what we would get. And let's remember what we're saying too. We're saying if the absolute value of x is less than 5, then the function 1 over x plus 5, that was the original format, right? Should be equal to this series, right? So let n be 0, what do we get? -1 to the 0, 1/5, x to the 0, 1. So we get 1/5 plus, now let n be 1. What do we get? It's actually negative, so how about we make that a minus? And then n is 1, so what? 1/25 x. Now let n be 2. So what are we going to get? Plus 1 over 125 x squared. We'll go one more. What? Minus 1 over 625 x to the third plus dot, dot, dot. And that goes forever, right? You with me? All right, so let's try something. If I ask you right now, what's f of 0? Everyone would just plug 0 in here and get what? 1/5? What about that? Plug 0 into this. What do you get? 1/5, don't you? So they're the same, aren't they? At 0, they're the same function, aren't they? And as long, excuse me, been dealing with this all day. As long as the absolute value of x that you pick is less than 5, then these two functions are exactly the same. The difference is this one's easy to evaluate, right? Just plug in the number. This one you'd have to go out forever, which you can't do. What is f of 1? Well, according to this, it's 1/6, right? But according to this, it would be what? 1/5 minus 1/25 plus 1 over 125 minus 1 over 625 plus, and you'd have to keep going, wouldn't you? What we're saying is that this sum right here should add up to be what? 1/6. If you were to get on your calculator and start doing this, I promise you it's going to get closer and closer to 1/6. The further out you go, the closer to 1/6. Are you checking it? Well, you're trying to? Let me know if you get something close to 1/6.
Eventually, we're just having a series that adds up for each value of x that we plug into that series, and they'll eventually approach what we actually get.
That's right. Okay? But the bigger picture is this. If this function is easy to evaluate, or not evaluate, if this function is easy to integrate, you would never need this. But if this function is not easy to integrate, this would be easy to integrate, wouldn't it? Like, let's say we had no idea in the world how to integrate this function. How would you integrate this? Just term by term, right? What's the antiderivative of 1/5? 1/5 x. That's a 5. Okay, what's the antiderivative of this? Minus 1/50th x squared. Then plus here, what? 1 over 375 x cubed. Minus, and you keep going, right? So the value of that is if I'm trying to integrate 1 over 5 plus x, and let's say I'm trying to go from 0 to 1, and I have no idea how to integrate that, what I will do instead is just use the antiderivative. This is the antiderivative, right? 1 over x, or 1 over 5x minus 1/50th x squared plus 1 over 375 x cubed plus, and I'll evaluate 0 and 1. And if I plug in 1, it's pretty easy to see what happens. I mean, you could just see it's 1/5 minus 1/50th plus 1 over 375. If I plug in 0, it's what? 0? Right? If I plug in, well, no, because I've integrated it. So if I plug in 0, they're all 0, aren't they? Are y'all getting this or not? I mean, it's this right here, this integral. If it's hard to do, we could do the power series of it, integrate that power series, and evaluate that power series. And the closer I need to, the more significant digits you want, the further I'll go out into this series. As close as you possibly ever want me to get. All right, we're done with that problem. Any comments? Anything? What came first? Power, what do you mean, between what? Integration, yeah. But there were limitations. There were certain things we couldn't do. So let's get to this function right here. Now we saw that Wolfram had a problem integrating this function, didn't it? I mean, well, it got it, but it was a mess. So what if we wanted to integrate this function, which is, I'm not asking you to, right? I don't have an integral sign up here. I just want you to first convert that to its power series. Can you convert it to a power series? Well, you got to make it look like this first. 1 over 1 minus u. So can we do that? 1 over 1 minus what? Negative 7, x to the 7. You don't need to factor out, like the last time we pulled a 5 out, here you don't need to pull anything out. Because you already have a 1 here, don't you? We had a 5 in the previous problem, so we had to pull a 5 out. Everyone got that?
Sir,
Yes.
would it just be safe to say that you pulled out a negative from the x?
Yeah, if you want. I factored out a negative from x to the 7th, sure. Or you could also look at it as, you know, addition is subtraction of a negative. When you subtract a negative, it's the same as adding. Okay.
No.
No? Okay. So this is true, right? This is true? And if the absolute value of what's less than 1? Negative x to the 7th, right? That's the part that we are going to be calling our u, right? That's the u in the problem. If that thing, if the absolute value of it is less than 1, then we can rewrite this function as a power series. And the power series will be the sum n equals 0 to infinity of negative x to the 7th raised to the n. And be careful because the negative has to be in there, just like it was with the negative 5, negative 1/5 earlier. And then from here, I'll start peeling things off. So I'm going to take a negative 1 to the n, and then I'm going to do x to the what? So I'm looking at as negative 1 times x to the 7th, which was to the 7th to the n, and I'm looking at that as negative 1 to the n, and then x to the 7th to the n, right? So I can write this as x to the 7n, can't I? And just to get used to this, let's write out the first few terms of this series. So that's equal to, let's see, let n be 0, what do you get? 1. It's going to alternate. If n is 1, it's negative, right? And then x to the 7th. And then it's going to alternate plus. And now x to the 14th. And then minus x to the 21st. Are y'all seeing this? Go one more. X to the 28th, and then minus, oh, I lied, x to the 35th, and plus dot, 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 right? But this only works, right? You can only turn that function into this power series if what? This is true, right? If this isn't true, this doesn't work. So we have to be within the radius of convergence. And so let's look at that radius of convergence now. Because we've generated the power series, right? Here are the answers. This is our power series. Here's the power series written out, first few terms, right? And the radius of convergence, yes?
Could we just do the radius of convergence first in order to figure out if we're wasting our time or not?
Sure. But the radius of convergence, I mean, you should have something. Like it's not going to be 0. Like no radius of convergence. You're going to have some radius of convergence. Do you know why? Yeah, because if I'm giving you a function, the only way it's going to have really a radius of convergence of nothing is if that function is only defined at a single point. Does that make sense? So we're always going to have some radius of convergence. It might be an interval, it might be the whole number line.
Oh, okay, so it'll never not work?
If we're taking a function that we already have defined and converting it to its power series, we should have a radius of convergence. We should have something. Or else the function you're giving me to start with is a joke, kind of, right? Now, if I just give you a power series and I don't tell you where it came from, then you could have a radius of convergence of 0, which is the previous section. So I'm taking this, I'm peeling off a -1, absolute value -1 won't matter. So this becomes absolute value of x to the 7th less than 1. And then you can take the 7th power outside the absolute value, and then you take the 7th root of both sides. And what's the 7th root of 1? It's 1. So our radius of convergence is still, what? Well, what is it here? 1? So the radius of convergence is 1. So that means I've got to pick numbers between -1 and 1 for this to work. All right? Now you might be saying to yourself, well, that kind of sucks because, you know, what was the original function? It was 1 over 1 plus x to the 7th. I'm telling you that you can approximate this with that power series as close as you want, as long as you promise me that the x's you plug in are between -1 and 1. So maybe you're like, well, wait a minute, what if I want x to be 2? Like if I plug 2 into this, can we get a number? But if we plug 2 into this, it's not going to work. Why? Because 2 is outside the radius of convergence, right? So you're sitting there going, well, what's the use of it, right? Well, what we can do and what the next section deals with is that what we do is we shift the power series over. And we can move the power series closer to another number. And the way we would do it is just simply doing like a -2 in here or something, and that would move it over. That would move the whole function over. So there's a ways around it. All right. So now, if I ask you to integrate this, even though we can't do it algebraically, what we could do is we could say, all right, well, that's the same as integrating, what was it, 1 minus x to the 7th plus x to the 14th minus x, is this right?
Yes.
Plus,
28.
was it? Am I? Okay. Right? That's an infinite series sitting inside of an integral, right? Like that. Now, I can do this so long as what? As long as this is true, I can do that, right? And so now, integrate term by term. You get x minus 1/8 x to the 8th plus 1/15 x to the 15th minus 1/22 x to the 22nd plus 1/29 x to the 29th. You with me? 1/36 x to the 36th plus dot, 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 right? That's what that would be. Plus a what, though? Plus a constant. A lot of times we put the constant out at the front instead of the back because the back keeps going forever, right? So a lot of times books will put like c plus and then x and then the rest. I always throw it on the end, but okay? That would be the antiderivative, right? And so if you were asked now to integrate, let's say, between 0 and 1/2, could we do that? Yes, because 0 and 1/2, that interval, lies in here, doesn't it? So this would hold. So what I would first do is I would plug 1/2 into this, right? Compute it. And then I'd plug 0 into that, which would just be 0. And then whatever that answer is, that would be the numerical equivalent. Understand? Do you want to do it? I don't feel like doing it. You plug 1/2 into all these. So if I go back over to Wolfram Alpha now, and I ask it to integrate 1 over x to the 7th plus 1, and I say from 0 to 0.5, it should give me a numerical answer, shouldn't it? .499514. Well, guess what? If you plug in 0.5 right here, and 0.5 here to the 8th, and all that, and do all this on your calculator, you should be really, really close to .499514.
So what's the answer?
What do you mean? That's the answer. Yeah. So what Wolfram Alpha did is exactly what I just did, what we just did. That's what Wolfram Alpha did. It converted the integral into a power series. It integrated the power series, and it evaluated the power series. That's how it got the answer. In fact, if you scroll down, a lot of times Wolfram Alpha will have a lot of other things in here. No, let me just type in, I'm not going to type in integrate. I'm just going to type in 1 over x to the 7th plus 1. And just watch, let's look at some of the things that come up. There it is. Oh, there's its graph, okay. There's always other stuff down here. Oh, whoa, whoa. What is that? Series expansion at x equals 0. Isn't that this right here? See this? See these two right here? Okay, so what Wolfram Alpha is doing is it's saying, okay, I'm giving you the first two terms of its series, power series. That OX13 means it went out as far as the 13th power of x and it stopped. The next one appears at what, 14? So you could actually have the computer go out. I mean, Wolfram Alpha is only going to give you that much. You probably have to pay to get the whole series if you want the whole series. You all understand? Now, I have a program. I told you the brains of Mathematica, or Wolfram Alpha, come from this program, Mathematica. And if I go in here and I just type in series and 1 over x to the 7th plus 1, and I want my variable to be x, and I'm not going to move it. Remember how I said you could shift it? I'm not going to shift it. Damn it. So I'm going to leave it at 0. 0. And how far do we want to go out? If I go 13, it's going to give me exactly what Wolfram Alpha gave me. See that? One. Yeah, I don't know why it says 14 here. But if I go, how far did we go? 30, 35? So what if I put 38? I should get the first, I should get all these that we just got, right? The ones that we just got right here? Okay. Makes sense? All right, next example. Same thing. We want to rewrite this with the power series. Let the fun begin. All right, now this is all we have to work with, right? And that looks nothing like this, does it? 1 over 1 minus u. So maybe you'll agree with me that this is equal to this. How did I do that? Partial fractions. Partial fractions. Remember how we split that apart? We did this when we were trying to integrate things. So I'm not showing this step, you know, where you have to find the A over this, B over this, and figure out what A and B are. Yeah? Yes?
Did you do this in your head?
I have this pre-done. Yeah, this These lectures are kind of have to be thought out a little bit before. Yeah, no, I had this all pre-done. Yeah, the stuff we're starting to get into now, it's hard to have it all up there. It's a lot of information. So, all right, yes, we good? Now, each one of these could possibly be written like that, right? This one, well, let me try and tweak it. How about this? How about, what can I do to this? I can rearrange it. If I rearrange it, it'll be this, won't it? And then on this one, I'm just going to leave it as 1 over, let me rearrange it, 1 plus 2x. So all I'm doing is rearranging so I can get my variable on the right side, on the bottom. And now, what can I do to this one? Pull a negative out, right? If I pull a negative out of the bottom here, can I slide that negative to the top? Negative 1 comes out, that negative can go on top? Yeah. Yes? So negative 1 on top, and on the bottom, 1 minus x. So I factored the negative 1 out. That negative 1 went to the top, went back through as a negative 1. And then on this one, I just need this to be a 1, which I have, and I need this to be minus. So I can rewrite it as, let's see, minus, and then 1 over 1 minus negative 2x. Y'all see it? It's just algebra. All I'm doing right now is just algebra, right? This part right here is like the u in that formula, isn't it? I'm going to call it u1 because I have another one over here. It's a different one, isn't it? This is a u, a different u. I'll call it u2. So I have two different series here, don't I? This is going to turn into a certain power series. This is going to turn into a power series. As long as what? The absolute value of that's less than 1 and the absolute value of that's less than 1. Both of them. Yeah, that's going to affect when we rewrite this as a series. All right, we good? All right, so here's where we are. If the absolute value of x is less than 1 and the absolute value of negative 2x is less than 1, then the original function will turn into this minus this, right? So on this one, I'm going to pull the negative 1 out. So that negative 1 is coming out, which leaves me with 1 over 1 minus x. What does 1 over 1 minus x turn into? Sum n equals 0 to infinity of x to the n, right? Everyone see that negative 1? I didn't want it there, so I just popped it out. Okay, over here, I'll have a minus sign, sum n equals 0 to infinity, and then what goes in there? Negative 2x to the n. Now you might think you're done, but you're not because this is two series, right? We want our answer to be a single power series. So one summation, not two summations. So let's try cleaning this up a little bit. Can I do this? Negative 1 bracket sum n equals 0 to infinity of x to the n plus sum n equals 0 to infinity of negative 2 to the n times x to the n. So what did I do here? What did I do? Actually, you know what? I want to do one more thing here. Sorry. Don't get mad. Negative 1 to the n, 2 to the n, x to the n. Is that all right? I decided to peel that negative 2 apart a little bit more. That's, yeah, what happened to it. So this has a negative in front, and this has a negative in front. So I pulled the negative out of both of them. And now if this negative were to distribute, it would go in front of this one, right? and then it would go in front of that one. That's why that turned into a plus. Yeah? No questions on that? We're still working here, all right? I need a single sum, so let me see if you follow this now. I'm going to leave that up there because I have to figure that out in a minute. This is equal to, let's say, -1 bracket. How about this? Sum n equals 0 to infinity of 1 plus -1 to the n, 2 to the n, x to the n. Whoa, what just happened? I went from 2 sums to 1 sum. Yeah, what do these 2 sums have in common? They both have this, right? So if I were to take, look at this expression right here. If I were to take this x to the n and distribute it through this parenthesis, wouldn't it go here to this 1, and then wouldn't it go to these guys right here? And so you'd have, what, x to the n? And over here you'd have all this junk x to the n inside of a sum, which means you can split it into 2 sums. So we're going backwards from this to this. That makes sense? All right, one more thing I'm going to do. I don't like that -1 sitting out there. I'm going to pass it back through. So what happens if I come through here with this -1? So this equals, no more bracket here because I'm passing a -1 through this sum. It changes this to a what? -1. And then this, be real careful here. If I multiply -1 times this, it'll be what? -1 to the what? n plus 1. And then I still have there 2 to the n, right? But all of that multiplied times x to the n. Do y'all follow that through, that negative going through? Everyone understand where this came from? That's here to here. Everyone understand where this came from? What happens when I multiply that times -1? What's -1 to the n times -1 to the first power? -1 to the n plus 1, right? That's where that comes from.
It doesn't affect the 2 at all?
No. And that was the thing I was going to ask you. Why doesn't -1 hit this? This all goes back to, basic algebra. Look, if I tell you 4 times 3 plus 2 times 5, and I say distribute that 4 through, you'll do what? 4 times 3. And then are you going to do 4 times 2 and 4 times 5? No, you're just going to do 4 times 2. And if I throw an x on the end of this, are you going to pass that 4 all the way through to the x? No, it's just going to go through one of these. Right? It's either going to go here or just to the x. So you have to be careful with, algebra. Yes?
Why don't we just put a negative instead of a positive?
Where?
Where you distributed the negative sign? Yeah.
Why don't I do what?
Why don't you replace the positive? Yeah. with
You
the-
could have. Yes, you could have. You could have done that. There's going to be many different ways that your answer could look. The thing that won't change is that if we start to ask you to write out the first few terms, we should all have the same thing. All right? So let's do that. Let's write out the first few terms of this. Let's let n be 0. What do you get? All right, so this piece, this is our c sub n. This is our x minus a to the n, right? So let's see what happens. If n is 0, we get what? We have to do order of operations here. So this is n, 2 to the 0 is 1. -1 to the 1 is -1. So all this together would be what? -1, and then plus -1 is -2. And then x to the 0 would be 1. So the first term should be negative 2. Okay? Plus. Now let's let n be 1. So what happens if n is 1? This is negative 1 squared, so it's positive 1. 2 to the 1 is 2. So we're getting a 2 here. Minus 1 is going to be 1. But then x to the 1, x. Y'all are all looking at me like I'm doing some crazy stuff up here. Let n be 2. 2 plus 1 is 3. What's negative 1 cubed? Negative 1. Okay, I'm plugging in what now? 2. 2. Plugging in 2. 2 squared, 4. What was that? Negative 1. So negative 4, negative 5, x squared, and so on and so forth. Yeah? Now, I'm going to check it. What was the original function?
X plus 2 over 2x squared.
X plus 2 over
2x squared.
2x squared minus x minus 1. I'm not going to go out the first 38. I'm only going to go out the first 5. There it is. Did we get it? It looks promising, doesn't it? We got the first 3, right? So we should feel pretty good about that. So you're sitting there going, well, that can do it. Why are we doing this? All right, what's my radius of convergence? I need to do some work on this one, don't I? This is the same as absolute value of 2 times absolute value of x less than 1. This is the same as 2 absolute value of x is less than 1, which means absolute value of x has to be less than 1/2. Agreed? The other one, absolute value of x is less than 1. So what's our radius of convergence? What do you think? 1/2? See, look, in order for that first series to converge, x had to be, the absolute value of x had to be less than 1. If you look at that graphically, here's 0, here's 1, here's negative 1. The first one, this one, said that we had to live in here for it to work, right? But the second one said we have to live in here for it to work. So we have to choose the smaller of the two intervals. Because if I say negative 1 to 1, I pick a number here, this one's okay, right? But this one's not. So you have to take the smaller of the two. So our radius of convergence would be 1/2. Good? All right. This is a theorem. This is what we call term by term. Differentiation. And integration of series, of power series. Suppose f of x equals the sum n equals 0 to infinity c sub n x minus a to the n, with r being greater than 0. So what am I telling you there? Suppose we have a power series that has a radius of convergence that's greater than 0, which means that there is some interval, right, where this thing is going to make sense. Remember how we talked about the radius of convergence, told us something like about the domain of the function? So we're talking about a function that can be represented as a power series and that it has some domain other than just 1 point, 0. So it's got some interval as a domain. All right, suppose that's true. Then we have the following. 1. F is differentiable on A minus capital R, A plus capital R. So let me try and explain what this is saying. This A right here was the center point of our interval of convergence. If you look at a number line, A is right here. The radius of convergence being R means that we have some interval where this is A plus R and this is A minus R. Does that make sense? Here's the center of your power series interval of convergence. Here's that center plus R, here's that center minus R. So this theorem says that if this is a power series that has a radius convergence that's greater than 0, then it's differentiable. You can take the derivative. All right? Ron? What's up? Tired? Go run around. Do like 10 push-ups or something. All right, so it's differentiable. Well, if it's differentiable, I wonder what the derivative is. Don't you? No? What's the derivative? Well, let's write out what f is.
1.
Tell me what f of x is. Give me this power series written out, the first few terms. Tell me what it is. So let n be 0 and tell me what you get. C sub 0. So some number, right? And then x minus a to the 0, which is just 1. So is that okay if I just put c sub 0? Yes? Plus c sub 1, x minus a to the 1. Plus c sub 2, x minus a to the 2. Plus c sub 3, x minus a to the 3rd. I'll do one more. Plus c sub 4, x minus a to the 4th. Plus, keep going, right? So what's the derivative of this? If I say, all right, what's the derivative? What's the derivative of a constant? 0. Plus, all right, be careful here. This is a constant, so just bring it down. What's derivative of x minus a to the first power? What's derivative of x minus 5 to the first power? Oops, to the first power. What's the derivative of that? Derivative is just 1, isn't it? Just 1? Yeah? So bring the c1 down. Derivative of that is just 1. So c1 plus. Now here we have a little bit of a different situation. What's the derivative of, we're bringing the c2 down, right, as a constant. What's the derivative of x minus a squared? 2 comes down. Subtract 1 from the power. Take derivative of what's inside. So what should I have here? 2c2 x minus a to the first power and then times 1, which I don't need to put. What's the derivative of the next one? 3c3, c sub 3, x minus a to the second times 1 again. Last one. 4 c sub 4, x minus a to the third plus dot, dot, dot. Yes? That's what we would get? Now, I would like for you to tell me now, still working with this, I'm just out of room. I'd like for you to tell me what this series is in sigma notation.